Okay, so this is a quick video on solving rational inequalities, and you can find some of this same information in your lab manual. And I'm going to just talk you through this problem, and the steps are written here, so we're just going to follow those. We want to set one side of the inequality equal to 0. So we're going to take this 2x minus 1 over x plus 2. We need to subtract the 1. So we will have a 0 on the right side. And then we need to combine all terms into one rational expression. So as of right now, we have two terms, and we want to get this to one term. So we're going to have to get a common denominator and do the subtraction so that we are in one term. So our common denominator will be x plus 2. And then we will have 2x minus 1 minus, and then we need to multiply that x plus 2 into the top of the second fraction. And then we need to simplify the top of the fraction. We need to take the subtraction through. And continue simplifying. 2x minus x is x. Negative 1 minus 2 is going to give us a minus 3. Put this over our denominator of x plus 2. And we have gotten this into one rational expression, so we can check off that second step. If there's any factoring that you can do on the top or the bottom, you should do that now. In this example, nothing factors, so we are done with that step. And then you want to look at your restrictions, okay? So let's think about what we're doing here. If we had a graph, okay, and this is a rational function, we would be interested in the vertical asymptote, right? The vertical asymptote would be x equals negative 2. And so you'd have a vertical asymptote there, which means we have a restriction, right? X cannot be negative 2 in our domain, okay, because that's a vertical asymptote. And we would also want to think about, do we have any holes or any other things on our graph that we should be worried about? In this particular case, we do not have any holes. We will have an x-intercept at 3. Okay, so we want to just keep thinking about the graph here. You'd have an x-intercept at 3. We could also find a y-intercept, right? A y-intercept would, think about putting in a 0 here and here. You would get negative 3/2. So a y-intercept would be somewhere down here. Okay. We would have a horizontal asymptote at 1, y equals 1. And then we could start sketching. We know we're going to have something down here, right, because of the y-intercept and the x-intercept. Then we could plot another point, and we're going to have another curve up there, okay? So when we are working with an inequality, okay, we have an inequality here, we are interested in parts of the graph that are going to be above the x-axis, above because of the greater than sign. So that's going to be this curve on the left, and this part of the curve over here. Those are the parts of the curve that are above the x-axis. Okay, so I could go ahead and write my answer based off the graph here. Okay, I could say it's going to be negative infinity to negative 2, representing this left curve, union 3 to infinity. And notice I use a parenthesis here because we are interested in above the x-axis, not on the x-axis. If it was on the x-axis, we could use a bracket. All right, but most of the time you're going to want to probably just do a sign chart test or a number line test on it. Even though you can do the graph, sometimes the graph can get complicated and you may have a difficult time figuring out exactly what to graph. So if you're doing your number line graph, you want to make sure you plot your vertical asymptote. And you want to make sure you plot your x-intercept. Okay. And you want to think about, it's always going to be open circle fix that. Oops, geez. It's going to be an open circle at a vertical asymptote. At your x-intercept, you could have an open or closed circle depending on the inequality sign. This one's going to be open because it's a greater than sign. And then you want to check points in each interval. So if I want to check this first interval on the left, I could use an x value of -3. And then we're going to take this statement here and plug a -3 into it. All right, and simplify this down. So you're getting -6 on the top and you're getting -1 on the bottom. That simplifies to 6. So is 6 greater than 0? Yes, it is. Okay, so I'm going to highlight this section since that section checked. Okay, and then we would continue checking other intervals. So I could check this interval in the middle. So that would be maybe an x value of 0. Plug in your 0. And is that greater than 0? Is -3/2 greater than 0? No, it's not. So we are not going to use this section. All right. And then we'll check this interval on the right side. We'll use a value of 4. Plug that in. And you're getting 1/6. And is 1/6 greater than 0? Yes, it is. Okay, so we're going to highlight that section since it worked. Okay, and essentially what we've done is we've highlighted the sections of the graph that are the answer. So that's going to be -∞ to -2, parentheses, union, parentheses, 3 to infinity, which is obviously the same answer we got up there. Okay, so essentially in a quick little recap, you can get the answer from your rational graph or you can get the answer from your sign chart method. Going back to the steps up here, what they were doing is talking you through the sign chart method. So you can see they actually referred to the sign chart here in this section. So we did the sign chart and the test and number in each interval, and then we wrote our solution in interval notation. And here in the middle is where it's talking about what numbers to put on your sign chart or your number line. And you have to think about your restrictions. Okay, so remember that was our vertical asymptotes that we were talking about. We restricted our graph on vertical asymptotes. And you also want to think about your x-intercepts, and that's where the function is set equal to 0. Those are your x-intercepts. So either method is okay. All right, if you think you want to do the graph, then practice that. If you think you want to do the number line, then practice that. And understanding both methods allows you to switch back and forth between the two if you would like to do so.